Hello everyone, let's start the new section. In this section, we study the magnetic field produced by a current carrying wire. It's given by a basic experimental law, the Biot-Savart Law. We now develop a procedure for calculating the magnetic field due to a specific current distribution. Before considering the magnetic field, let us first review the analogous procedure for calculating electric fields. We consider a charge element dq. It sends up an electric field dE according to the Coulomb's law. To find the total electric field E due to the entire distribution, we just integrate over Q according to the superposition principle. In the case of magnetic fields, if we know the way of how the current elements procedure produce magnetic fields, so the total magnetic field generated by an arbitrary current carrying wire can then be calculated. We seek the force between the two elements. We also hope to find the rules of how current elements produce magnetic fields. Now, how a current element IDL can produce the magnetic fields? The Biot-Savart Law answers this question. According to the experiment results of a Biot-Savart Laplace deduced its mathematical expression from the mathematics, so the law is also called Biot-Savart Laplace law. In this expression, the constant μ0, called the permeability constant, has an exact value. μ0 equals to 4 pi times 10 to minus 7. The permeability constant μ0 plays a role in calculating magnetic fields similarly to that of the permittivity constant epsilon0 in calculating electric fields. The two constants are not independent of one another. They are linked through the speed of light c, such that c equals to 1 over epsilon0 times μ0. For any section of current carrying wire, we select the current element IDL, which generates a magnetic field at point P, where the position vector of P is r, and the angle between r and IDL is theta. The magnetic induction intensity at P is proportional to IDL and sin theta, and inversely proportional to r squared, and the direction is given by the right-hand rule of cross product. Let's give some examples of how to determine the direction of the magnetic field. If the current element IDL is horizontal to the right, the direction of the magnetic field B at point P is perpendicular to the screen and points outwards. If IDL is vertically inward at the up point, B points to the left. If point P is on the extension line of IDL, then B is equal to 0. We now consider how to apply the Biot-Savart law to calculate the magnitude fields of some current carrying wires of different shapes. Firstly, let's consider a current in a straight wire segment. The figure shows a straight wire carrying a current I. We want to find the magnetic field at point P, located a distance from the wire. According to the Biot-Savart Law, the first step is to choose an arbitrary element of where IDL. It established a field dB at a point P. The position vector is r, and the angle between them is theta. The magnitude of the contribution dB of this element to the magnitude field at P is found from its equation. The directions of the contribution dB at point P for all elements are the same, namely into the plane of the figure at right angles to the screen. This is the direction of the vector product dl cross r. We can thus evaluate a scalar integral rather than the vector integral, and B can be written in this form. Let's evaluate the scalar integral. Set up a coordinate axis. Select the origin of the coordinate O. The positive direction is along the current direction. The distance of current element is L. The angle between the positive vector from the lower end to the point P and the positive direction is θ1, and the angle between the position vector from the upper end to the point P and the positive direction is θ2. From the figure, we can get the geometric relationship between A and R, and the relationship between A and L. Taking differential opposition on the second formula to get the expression dl, and substitute them into the scalar integral above. Now, the integrand is expressed as a function of A and theta. The integral ranges from θ1 to θ2. Since A is a fixed value and the sign function is easy to be incremented to obtain the final expression of magnetic detection intention B and point P. Its magnitude depends on the distance A, angular position θ1 and θ2. The direction is perpendicular to the screen point inward. From the expression of magnetic field B due to a current in a straight wire segment, we can have some extended discussion. If the wire is an infinitely long wire, angle θ1 will tend to 0 and θ2 tends to pi. The field B becomes the simple form. The strength of the field depends only on the distance from the field pointed to the wire A. To find the direction of the field line, we use the right-hand rule. If you were to grasp the wire in your right hand with your thumb in the direction of the current, your fingers would curl around the wire in the direction of the magnetic field. If a long wire is bent into the shape shown in the figure, it can be regarded as a two semi-infinite straight wire placed at 90 degrees. Let's take the turning point as the coordinate origin O, and the distance from the point P to the origin O is A. P is on the extension of wire 1, so current 1 does not contribute to the field at point P. Thus, B1 is equal to 0. The current I2 is a semi-infinite wire. Using the general formula above, we take θ1 equal to 90 degrees and θ2 tends to 180 degrees, and we get the expression of B2. As you can see, it's half of the field strength of an infinitely long straight wire. According to the right-hand rule, the direction of the magnetic field at point P is perpendicular to the screen outwards. We can also extend the infinite length of the wire to the infinite length of the flat plate. We consider the infinitely long plate as shown in the figure, carries a current I and its width is b. Establish a coordinate axis. The y-axis is along the symmetry axis of the plate. Let's consider the field point P on the y-axis. Take a current element on the plate with a cross-sectional with dx. Its contribution to the point P can be regarded as a magnetic field generated by an infinitely long straight wire. Let's solve this problem according to the superposition principle. The current carrying element of a wire with width dx is di. Its vertical distance from point P is a vector r, and the point P, the magnetic field dB, is generated, and the direction is perpendicular to the plane formed by I and R, pointing diagonally downward in the figure. Its magnitude is an expression of the infinite wire discussed earlier. According to the geometric relationship, R is projected to the coordinate system, where theta is the angle between the R and the y-axis. In this way, dB is expressed as a function of dx and theta. Next, we consider the current element symmetrically to the dx on the other side of the plate, as shown in the figure, which produce a magnetic field of dB prime in a diagonally upward direction. According to the symmetry analysis, the direction of the combined vector of dB and the dB prime is a negative direction of x. The sum of the vector along the y direction is 0. Then the total field of the point P has only the x component, and the magnitude of the integral dBx. Take the projection of the dB on the x-axis, thus to multiply cosine theta, and we get the expression in terms of dx and theta. According to the geometric relationship, dx is expressed as theta, so that the integrand is unified into an integral variable theta. The range of theta integral is from 0 to theta 1, and the expression of theta 1 can be obtained from the geometric relationship in the figure. Thus, we obtain the magnetic field distribution of an infinitely long current carrying plate along its axis of the symmetry. Let's have an extended discussion on this result. If y is much less than b, which means P is far away from plate, then arctangent B over 2y will approach B over 2y, and the magnetic field expression BP will return to the case of the infinitely long straight wire. If y is much less than b, which means P is very close to plate, so B over 2y approaches infinite, and the arctangent infinite approaches pi over 2. Then expression for the magnetic field BP becomes very simple, independent of the distance y and dependent only on the linear density of the current I. This is a magnetic field generated by an infinite plate carrying current. Consider two infinite plates placed in parallel and shown in the figure. We divided the space into three regions. one current is upward and its other current is downward. So the direction of the magnetic field generated by the plate on the left is shown here. The field on the left side of the plate is pointing outward. The field on the right side is pointing inward. The magnetic field generated by the right plate points inwards on the left side of the plate and points outward on the right side. According to the principle of the field superposition, the fields located in area 1 and 3 just canceled out to 0. There is a uniform magnetic field in the inner region, too, which is twice as large as the contribution of a flat plate, and it is directed inward. This can be regarded as a magnetic shielding effect. That's all for the section. Thank you for your attention.